Guillaume Barraquand, who's going to talk about last passage percolation in a strip.
Thank you. I am very happy and honored to be speaking here in this conference for Philippe's birthday. I don't have any cool picture of Philippe. I only have a picture about math. And so this was a discussion about McDonald polynomials, and this illustrates one of the areas of interest of Philippe. And it's also related to this talk in the sense that I want to explain a connection between integrable probabilistic models and symmetric functions. Except that, this discussion was about McDonald polynomials, so where Philippe told me about McDonald polynomials in types other than A. And today we will discuss about symmetric functions, which are much simpler, only the Schur functions and the most standard Schur functions. So I will start by explaining well-known things, mention a few open problems, and then some new results. So I'll start with the math side, with the symmetric function side, and recall a few things about Schur functions. So the Schur functions S lambda of x can be defined as this ratio of determinants, where lambda is an integer partitions, the lambda i's are ordered, and x is some set of, say, n variables. And it is well known that Schur functions, they satisfy nice identities, nice summation identities, so you can take the sum, so you can take a Schur function in the variables a1 to an, another Schur functions in the variables b1 to bm, take their product and sum over all partitions, and it turns out that this has a very nice product form expression. So this is called the Cauchy identity, and this product here I will need to reuse it, so I denote it by pi ab. Another famous properties of the Schur functions is that they satisfy some branching rule, and here I have not written what is the branching rule, but the branching rule allows to expand those symmetric polynomials, so this S lambda of x are polynomials, and they are symmetric with respect to exchanging variables, and we can also explicitly expand them into monomials. So the explicit expansion into monomials is written here. It's a sum over sequences of integer partitions, lambda superscript 1, lambda superscript 2, etc., that are interlaced. And here interlacing means that, so mu interlaces with lambda if we have an ordering of lambda 1, mu 1, lambda 2, mu 2, etc., etc. So with these two things, now we can play a bit, and then I will tell you what one can do probabilistically. So here I rewrote on the top of the slide the Cauchy summation identity, and one thing that one can do is expand both sides, which look quite different, into monomials and try to interpret that. So as I said, each Schur function S lambda is a summation of monomials summed over a certain sequence of interlaced partitions. So on the left-hand side, if we sum into monomials, we'll naturally see arising two sequences of interlaced partition that end up in the same partition lambda. So that's what will arise in the left-hand side of the Cauchy summation identity if we expand. And I didn't write the expansion in monomials of the right-hand side. In the right-hand side, we first have a product, and then we have something which is very easy to expand in a power series, and then we can exchange the series and the products, and we will very naturally get an expansion over matrices with integers, so an array of integers of size n by m. So since there is an equality between the two things, there must be a bijection between those monomials on each side, and one way to relate the monomials is called the Robinson-Shenstedt-Knuth correspondence. So which is indeed a bijection between sequences of interlaced partitions and matrices filled with integers of size n by m. So this Robinson-Shenstedt-Knuth correspondence is usually defined in another way as in terms of semi-standard Young tableau, and there are several variants, and it has a more combinatorial definition. Actually, what I've written here is not a definition. And there is one result about this Robinson-Shenstedt-Knuth correspondence called Green theorem, which implies in particular that certain, so under this map, the map is complicated in general, but certain coordinates, say, of lambda have a nice interpretation in terms of the matrix W. And one example is lambda 1. So lambda 1 is the largest part in the partition lambda. And this one has a very nice interpretation in terms of the matrix entries Wij. So if you put the matrix entries on the vertices of a certain grid, n by m grid, like here, then lambda 1 will correspond to counting sums of weights along paths. So we consider all the paths which go from one corner, the corner 1, 1, to the corner nm in that grid and progress upright. For each path, we look at the sum of the integers wij's along that path, and lambda 1 will turn out to be the maximum over all possible paths between 1, 1 and nm. And this quantity, I will call it G and M in the following. So because of this RSK correspondence and because of the skew of the Cauchy summation identity, one can now probabilistically interpret the identities by matching by looking at all the monomials as certain probabilities that a certain matrix arises. And so if one does that, the correct law to put on the matrices is to assuming that Wij's, all the Wij's are independent, and they are distributed as geometric random variables, geometric with parameter AI, Bj, and so here, geometric of parameter q means that the probability that the variable is equal to k is proportional to q to the k. If one does that, then it's really a direct application of the RSK correspondence and the Cauchy identity that the probability that G and M, so this maximum over paths of sums of random variables, the probability that this is less than some value R will be given as a sum over partitions, summing only over partitions such that lambda 1 is less than R of a product of two Schur functions. So another way to state that is that lambda, so G and M, this last passage percolation time, this is how it's called, has the same distribution as lambda 1 when lambda is sampled according to the Schur measure, that is the measure on partitions proportional to S lambda of A, S lambda of B. The pi AB is something that we need to normalize this as a probability measure. So here, this thing was the pi AB, so if we divide everything by pi, we get 1, so that this is indeed a probability measure. So these ideas were the starting point of a paper of Johansson, who proved that as n and m goes to infinity, G and M has very interesting fluctuations. It doesn't satisfy a central limit theorem, but it has fluctuations on the scale n to the 1/3, and the limiting distribution is the Tracy-Widom GUE distribution, which arises in the fluctuations of the largest eigenvalues of Hermitian random matrices. And then, shortly after that, several variants of this result arose. In particular, variants where the matrix of weights has symmetries. So there is a series of papers of Bike and Rains who studied this. The first variant that one can use, which is very natural to do from the perspective of RSK, is to assume that now in our matrix of weights we have a symmetry axis, which means that Wij equals Wji. Then to make the model integrable, we have to specify some slightly different distribution on the weight. So Wij will be geometric of parameter AI, Aj. This time we have only one single family of inhomogeneity parameters, and we have a parameter on the diagonal. So on the diagonal, the weights Wii, they are geometric of parameter C times AI for some C. And then again, we define exactly the same last passage time, G and M, and I put a superscript to denote that the fact that the matrix now is symmetric. And again, the probability distribution of this last passage time can again be written very, very explicitly as a sum over partitions of some Schur polynomial, except that it's slightly different. Here, the normalization phi of A is defined by this expression, which is generally referred to as the Littlewood identity for Shor polynomials. And so indeed, this result is based on the Littlewood identity for Shor functions and on RSK when applied to a symmetric matrix. Sorry? Thank you for the question. So you can assume that the paths, they go wherever they want, but you can restrict to paths that stay below the line because you're looking at a maximum over all the paths and you sum the paths. But for any path that would go above the line, there is another path that does the same thing below and has the same energy.
Yeah, but aren't you then assuming that n is equal to m?
Yeah, well, here, yes, on this picture, yes.
Okay.
And so using this formula, then Bike and Range showed that the asymptotics of now G and N. Oh, yeah, sorry, actually, this was correct only for n equal m. But there is also a formula when n and m are different, and it's not that complicated. So asymptotically, one can show that the fluctuations of G and N now follow not the Tracy-Widom GUE, but the Tracy-Widom GOE or GSE distribution, so variance for symmetric real matrices or quaternionic matrices. And the two cases depend on the value of C. When C equal 1, this is a critical case where the diagonal weights are quite large, and this slightly influences the distribution, and we get some Tracy-Widom GOE distribution. But there are many other ways that one can impose symmetries on the matrix of weights. So one way, for instance, would be to consider a symmetry axis, but in the other direction. And Bike and Range also did that, and they also found a formula for G and M in terms of symmetric polynomials. And then they continued. They also looked at what happens when we have two axes of symmetry. And again, there is a nice answer in terms of symmetric polynomials. And there is another case that works well. This is a symmetry by rotation by 180 degrees. Or the composition between the two reflections. Again, by imposing this symmetry, there is a nice expression for the probability of the last passage times. There are, however, cases which we don't know how to solve. We don't know how to write the probability distribution of the last passage times when, for instance, we have a symmetry with respect to a line, but which is shifted, which is not really the diagonal line. Or maybe it's on the diagonal, but it's only a segment. It doesn't, we don't impose a symmetry on whole of the weight matrix. These two cases are open, and another case which is open is this one when we impose two symmetry axis, or coming back to your question, it also corresponds to assuming that here the paths that go from here to here, instead of imposing this symmetry on the weights, we can just impose that the paths stay between two walls. So we don't know how to write the probability distribution in those cases, but I will focus now on the last case. So the last case, I call it last passage percolation on a strip. And even though we're not able to exactly express the probability distribution of last passage times, I think that there is some integrability and we can still do something. So the most general model should depend on n parameters, a1 to an, when now capital N is the width of the lattice. And now it depends on two parameters, C1 and C2, where C1 controls the, C1 is the, AC1 is the parameter of the weights on the left boundary, AIC2 are the parameters of the weights on the right boundary, and in the middle we take geometric variables with parameter AI, AJ, where I and J are taken modulo n. And now, so before I was defining last passage times as maximum for paths between 1, 1 and nm. Here I will adopt a slightly more general definition where I take some initial condition. I will assume that on this first row here, I can just fix what is my passage time, what is g. So I take some function g0 and I impose that gi0 is this g0, and then I define the passage time gnm at above still has a maximum over paths from I0 to NM, the same kind of paths that stay in the strip. Yes?
Why don't you have A's and B's?
This?
Yeah, why are there not A weights and B weights for vertical and horizontal?
This is because it was already the case here when I have only one symmetry axis. I don't have two families of weights. On that theorem, you see where would you want to put the second set of inhomogeneities? That's one way to say.
So they only prove the case when the A's and B's were equal to each other, basically.
Yeah. You have to.
In principle, there is a model which is more general.
Yes, and actually this one is, in some cases, this one is solvable, but the expression here would be much more complicated. There are works of Lecouvé, Azenas, and someone else, but they expand, the sum becomes a much more complicated sum, and the show functions become essentially non-symmetric show functions, or de mesure something, de mesure atoms, I think. So it's possible, but the result becomes much more complicated.
What is the role of the G0?
G0, so later I will tell you that I cannot exactly tell you what are the asymptotics of GNM, but I can tell you what is the stationary measure for this model. And to define this notion of stationary measure, I need to have this G0. So G0 is some sort of initial condition.
Because for the maximum, it doesn't play a role.
So here it plays a role in the max. You cannot take out the G0 because so here you have to understand this maximum as maximizing both over I and over the path. And so as I said, finding the distribution of GNM is some open problem. Oh, this is weird. Well, there was supposed to be colors, and there are actually colors on the computer, but not here. So the most interesting scaling to take is when capital N, the width of our strip, is proportional to little n to the power 2/3. And this is something which is well known because it's related to the Cardar-Paré-Sizang class of models, and so it's the same for all of the models in this class. And let's say that the parameters AI are all equal to A, and then we expect that there are three phases. So here the phases are written in the two axes are 1 over C1 and 1 over C2, the two boundary parameters. And so when C1 and C2 are rather small, here the boundary weights don't play too much role, and we expect that fluctuations are on the scale n to the 1/3 with some unknown distribution, and it's unknown for any model. While in the other phases, so here fluctuations will be governed by weights on one of the boundaries, and here by the other boundaries, and so fluctuations will be Gaussian. And each time in front of the fluctuations, we have n times some velocity, which depends on C1, C2, and L. And this is the only thing that can actually be computed rigorously for this model so far. So right now we cannot prove this picture, but we can say something about what is the large term asymptotics of differences of passage times of the form G. Well, it was supposed to be GT plus IT and GTT. So on level T, points at distance I, what is the difference of their passage times? And this is supposed to reach a stationary measure. So the problem becomes of finding the law of the stationary measure. What I mean by that, we have to find a law on G0 such that if we define GT of I as this GT plus IT minus GTT, then this GT will have the same distribution for all T. So in principle, this kind of thing, this kind of question is answered by a now very well-known method called the matrix product ansatz. So that was introduced in the context of interacting particle system, in particular for the asymmetric simple exclusion process, already in the 90s. It works very well for particle systems and for variance and in many cases. So here, it would be a little bit more difficult to apply because this this difference is GTI minus GT plus IT minus GTT can be unbounded anything in Z. So we will have a more complicated matrix product ansatz, but I will explain in the end of the talk that the method that I will explain, which is based on symmetric function, is not that different from this matrix product ansatz. And another advantage is that I will present a method related to Schur polynomials, which work very well for other models. So for instance, there is a variant of last passage percolation called the log gamma polymer, which is exactly the analog of last passage percolation if you replace Schur functions by Whittaker functions. As a limit, one can also study stationary measures of the Cardar-Paris-Ising equation through this approach. Models such as the stochastic six-vertex model also fit in that picture if we replace Schur functions by Halley-Toulouse polynomials. And so there is a whole variety of models that can be studied through the same approach, but I took the simplest case, which is Schur functions and last passage percolation. So what is the result? What is the stationary measure for those increments of the last passage percolation time? It is one possible definition is to express them in terms of reweighted random walks. So I just need to introduce two pieces of notations first. So here R will denote the points of a discrete random walk. So R of J for J between 1 and N. And I denote by P index Q random walk of R as the probability that R is a random walk where each increment, R of J minus R of J minus 1, is distributed as a geometric variable, and all of them are independent. So that's the geometric random walk. And once I have this notation, I define a certain operation. Given two random walk paths, I can make an operation on them, which is quite reminiscent from Pitman transforms. So R1 star R2 will be a new sort of random walk, which is defined like that, in terms of a minimum of R1 plus the increment of R2 between J and K. And then I will define a measure, a probability measure on two random walk trajectories, R1 and R2. These two are correlated. So I first take the probability for R1 to be a geometric random walk with some parameter depending on C1. I take the probability for R2 to be a geometric random variable with a parameter related to C2. And then those probabilities, I multiply them by some factor C1, C2 to the power R1 star R2, this operation at the endpoint. And then, of course, to make that a probability measure, I need to renormalize. And this defines a probability distribution. This can be proved. And it turns out that then the probability distribution of R1 under that measure is the stationary measure of the Markov process, of this last passage percolation with two boundaries. So it is actually the simplest definition of the stationary measures that I have. But arguably, it's still a bit complicated, and you may wonder, can you deduce anything from such a description? And the answer is really yes. And this is thanks to connections with the Schur functions. There is another way to describe the stationary measure, to describe those two random walks R1 and R2. R1 and R2 are related to a sequence of what I call signatures, so they are not exactly partitions. So more precisely, we'll have some sequence of numbers, some array of numbers, lambda 1j and lambda 2j. And R1 and R2 just corresponds to increments, lambda 1j minus lambda 10, and R2 is lambda 2j minus lambda 20. And then we put a probability distribution on these lambda I. So here, the lambda j's are just signatures with two ordered coordinates that are in Z. They can be negative. So these are not partitions. But we can define Schur functions indexed by such signatures. It's exactly as for partitions. And then the probability distribution that we put is a product of skew Schur functions like that, times two factors, which are quite similar with what happened for the probability measure of last passage percolation with one symmetry axis. So here we have signatures of length 2, so really the show functions are extremely simple. We only use skew show functions evaluated into one parameter, and so there is a very explicit expression like that. This model is similar to various probability distribution on random partitions that are variants of the show process. In particular, it's connected to the free boundary show process, except that here we have signatures, the parts can be negative, and also, I went a bit fast, but this is not really a probability measure, so this is an infinite measure invariant by translation, and so it becomes probability measure if we fix the value somewhere, and there are some subtleties. Okay, so here I explain just the connection between those complicated reweighting random walks and the show functions. It doesn't, so this description is not necessarily much simpler than the one in terms of reweighted random walks, but however, show functions have many properties. And so thanks to all the properties of show functions, one can prove formulas for the formulas that fully characterize the distribution of the stationary process. So my stationary process was R1, and so so here I wrote some formula for the generating series of the generating function of this random variable R1 of n, but I could write similar looking formulas that are fully explicit for the joint distribution of increments under that stationary measure, and it's just an n-fold or k-fold integral in terms instead of just one integral. And out of such computations, one can deduce things about the model itself. For instance, one can deduce that starting from the stationary distribution, the expectation of the last passage time j equal exactly n times some explicit constant, and that explicit constant one can write it explicitly in terms of some partition functions at n and n plus 1, and those partition functions are very explicit. If you're familiar with the matrix product ansatz, all those formulas should ring a bell there. So this part of the work is not extremely new. It looks like formulas that were obtained already in the 90s using the matrix product ansatz, and so it's not surprising that it works. However, for other models, more complicated models than last passage percolation, then the formulas become a bit more complicated, but we can still establish them, and it becomes a bit more interesting. I'm not sure how much time I have. Okay. No, but I knew that I would have to skip a few slides, and so I think I will conclude like that. So we have seen that I defined this two-layer show process, which is a probability measure on sequences of signatures, and the probability is a product of show functions, and I just stated the fact that this measure, two-layer show process, allows to describe the stationary measure of models, of integrable probabilistic models between two boundaries in terms of reweighting random walks. The problem, those stationary measures, they cannot be too simple because they are non-trivial spatial correlations. And so that's why it was not, we didn't expect it that the probability measure should be a simple Gibbs measure. And what is remarkable is that if we properly enlarge the state space, instead of looking at the Markov process that we want, we look at a Markov process on a bigger state space, and then the stationary measure become a Gibbs measure that is just a product of things, and those things become skew show functions. Another way to think about this is to say that one could have tried to apply the matrix product ansatz, and here the matrix product operators would have elements which are exactly skew show functions. And so another way to think about this is that those symmetric functions, they tell us a representation of the correct matrix product ansatz relations. And again, so I explained the simplest case, but the method is a bit more interesting on other models, such as the log gamma polymer and the KPZ equation, and there are other families of symmetric functions that enter into the same picture and that I'm currently working on. And so thank you for your attention, and happy birthday, Philippe.
Thank you very much for this nice talk. I have a general question. Can you tune your symmetric functions so that you get higher order Tracy-Widom fluctuations? So more general, these generalized area kernels of Majumdar share, and if you take the Freton determinant, then you will get higher order Tracy-Widom.
The multi-critical.
Yes.
No, so there is. I don't know for sure, but I don't think it would easily arise from last passage percolation, for instance, because it naturally arises in the Shaw measure. So but when we express the Shaw measure, not in terms of the variables AI and BJs, but in terms of power sums of those. And no, I don't know exactly how to tune the model to that.
Thank you.
Any other questions?
So what type of results do you want to find beyond the stationary measure?
The expression for the fluctuations of, say, GNN, when we have two boundaries and a strip of size, say, n to the 2/3. So there should be an analog of the Tracy-Widom distribution, which goes to the Tracy-Widom distribution when we send the size of the lattice to infinity, and which should have also various limits, the GOE, GSE. There should be a probability distribution that interpolates all those cases, and it's unknown. And I think it would also be interesting technically, because at a more technical level, for instance, if we wanted to solve TASAP, in principle, the probability distribution should depend on all the beta roots of TASAP. And so I'm sure that mathematically there should be some interesting structure behind in order to find that new probability distribution.
Okay, so if we want to have a chance to have a coffee break, maybe we should end it now. So thank you again.